Hello everyone. Today I would love to show you the integrating factor method for solving differential equations, which you will be definitely covering in IB analysis and approaches higher level, as well as at one point if you choose an engineering path, then definitely in your calculus course you will be covering this method. So you by far should already be familiar with the method of solving differential equations by the good old separation of variables. However, the problem is that this is not always possible. One key example is when we have this form of a differential equation. So we have the derivative with respect to x in this case, plus some kind of a function of x multiplied with our y. And this will be equal to some other function of x. Now, you may try to separate the variables. I will leave it as a task to you, but definitely what it will be shown is that it is actually impossible for us to nicely separate the variables just to isolate the x terms and the y terms. Now, you may also ask, hey, there's a y. We have always defined y as some kind of f of x. Sure, but from now on, try to more think of y as just the dependent variable instead of some kind of an expression for x. This is what we will find eventually. So we want to eventually find this f of x. So how does our dependent variable behave when we alternate the x? Then we will try to solve two examples, one purely mathematical, one applied to an engineering context for people who would like to challenge themselves a bit more. However, I would like us to look at this equation first. So the integrating factor is going to be this sort of a function, let's call it I of x, which will be defined as e to the power of the integral. I know it looks scary, but trust me, it is not that bad, of the function p of x integrated with respect to x. Now notice that p of x is nothing else than this function that we have right here standing next to our y. So this is very important. And as a quick guide to why this integrating factor works, I will show you very quickly the theory behind it to portray why do we even use it. So let's only focus on the left-hand side. So we have dy dx plus p of x times y equals to something. So let's just call it LHS as for left-hand side. So what is our goal is to multiply both sides by the integrating factor. So basically by this e to the power of the integral of p of x with respect to x. And what we will actually do by that is we still have our function dy dx times our integrating factor p of x dx plus, now this is where it gets a bit interesting, is p of x times the e to the power of the integral of p of x dx times y is equal to some LHS prime. So LHS prime will be nothing else than our left-hand side multiplied by our integrating factor. So this is something that we don't really care about for now. What we do really care about is this left-hand side here. Because what is actually spectacular about it is nothing else than a chain rule and a product rule altogether. So how can we actually look at this is in the following way. Imagine that this is our function I of x, right? As we have defined it previously. Now, if we want to calculate the derivative of our I of x, this is nothing else than the derivative of this integrating factor, as we have previously defined it. So it is going to be nothing else than the derivative of the outer function, which is e to the power of the integral, times the derivative of the integral itself. Now notice we have the derivative of an integral, so it is going to be simply just our function p of x, okay? So now let's focus on it a bit further. We see already that we have dy dx times this form. Let me rewrite it once again. P of x times e to the power of px dx times y. And now let's recall the product rule. So the product rule is for the derivative with respect to x of some product of two functions, f and g. It's going to be nothing else than just the derivative of the first function times the second function plus the derivative of the second function times the first function, right? So we have already defined one thing, especially that the derivative of this function, which is the integrating factor, that this will be equal to our initial function, so p of x, times the integrating factor itself, p of x times dx. So we have defined that already. Now, of course, we also know that the derivative of y is simply going to be dy dx. So notice right now in our integrating factor expression, this is nothing else than y derivative. This is obviously here just y. And then here, this part is our I of x. And then this part right here is nothing else than I prime of x. So what are we actually left with is, let me quickly recall, y prime times I of x plus y times I prime of x. Now notice that this is nothing else than just the product rule applied to our function y and our function I, which is the integrating factor. So this is nothing else than the derivative of y times I, or if you prefer, y times the integrating factor, p dx. So now we already know why we should multiply our function by the integrating factor, because it will be able to simplify our whole expression. So what we will be actually left with is d dx of y e integral p dx. Of course, note that p is still a function, it didn't become a variable. I just spared the x, is equal to our left-hand side or right-hand side, whatever, they're all equal, times the integrating factor, so e to the power of p of x dx. Now this we will be able to separate, but let's actually show it on the example in a moment. So what we will show is that we can move this dx to the other side by both side multiplication, and from now on we are left with the differential of y e to the power of this integrating factor, p of x dx, equals LHS times e to the power of this dx, and then we will be able to integrate both sides. So let's show an example. Let's start with the purely mathematical example for some people that prefer more abstract concepts, and then we will work with a more applied concept, which is going to be a case of a reactor. So here we have this function, and you can immediately notice the form. So we have the differential, or actually the derivative, times this x, and this x will be nothing else than our p of x. Why? Because it stands next to our y. This x, on the other hand, will be nothing else than our other function, q of x. Recall, here we define the q of x as the right-hand side. So, coming back to the reaction, to the equation, we have our form. Let me rewrite it so that it is clean. And we can right now define the integrating factor, which is simply e to the power of x dx. Because notice that this is our p right now. This is very simple to calculate. E to the power of x squared divided by 2. Now, you may ask, what about plus c? Isn't this important for us? Well, theoretically we can include it, but you will see later that we will have one more integration. And this one more integration actually spares the necessity for including this plus c. If you're operating on a definite integral, then sure. But here we are not really required to include this plus c. So we can cancel it out pretty easily. So we have actually derived a form that looks in the following way. Dy dx times this integrating factor, e to the power of x squared by 2, plus this x times e to the power of x squared divided by 2 times y is equal to x. Now that we have multiplied both sides by e to the power of x squared by 2, so x e to the power of x squared divided by 2. And this is our expression. I know it looks daunting, but trust me, it's very doable. We have these two terms, and we know that they will simplify in the product rule. These two terms will do it as well. So how does it look like in practice? We have shown previously that it will simplify to y times this integrating factor, so y times e to the power of x squared divided by 2. You can verify it for yourself, because the derivative of this expression is simply 2 times x divided by 2 times e to the power of x squared divided by 2, where these 2's cancels out, and we are left with identical expression that we have right here. So it all checks out. Okay, on the other hand side, we have a bit more of a difficult expression, because we are left with x times e to the power of x squared by 2. Now what can we do? We can multiply both sides by the differential of x, so basically move this to the other side, and we are left with this crazy expression, x squared divided by 2 equals x times e to the power of x squared divided by 2 dx. And what now? Now we can take the integral of both sides, and we are left with the integral of dy e x squared by 2 is equal to the integral of x times e to the power of x squared by 2 dx. Wow. Now you may actually ask the question, how do we even integrate this thing? Now, it may in the beginning seem a bit counterintuitive. However, this is some form of a variable. So let's call this variable zeta. So recall that the integral of 1 times any kind of variable will give you this variable back. Of course, plus c. Okay, so knowing that, we can actually say that this left-hand side is simply y times e to the power of x squared divided by 2. And also note that I will spare the plus c for now. Why? Because we have two integrals. So if this left integral, right here, gives me some form of a plus c, and then this one on the right gives me some kind of different plus c, these two c's that we have here will actually combine to some kind of a different constant. Okay. So on the other hand, we have a bit more difficult integral to solve. not a standard integral for sure, but we can actually look for two things. One thing is integration by parts. We see the product rule here, so maybe we can do it with integration by parts. Or there's a simpler way. We can actually know that there's some kind of an inner function that is vaguely similar to our product function. So let's do a substitution of x squared divided by 2 equals u. And of course we take the derivative of u with respect to x, and this is simply equal to x. And now how do I do it? I try to rearrange this expression to give me dx, just dx. So I get du divided by x equals to dx. Now this dx, check this out, it's the same here. And then this expression is of course the same as this one here. So we can substitute everything very easily to get the following expression. X times e to the power of u times, now our dx has become du divided by x, where these two x's cancel out. So we actually are left with nothing but a simple expression of y times e to the power of x squared divided by 2 equals to an integral of e to the power of u with respect to u, which simply equals to e to the power of u plus some kind of a c. And of course we can note that our e to the power of u can be re-expressed in terms of x, so this is x squared divided by 2 plus c. Now of course always we want to re-express our final answer in terms of x and having y just on the left hand side. So we can simply divide everything by e x squared divided by 2, giving us 1 because it cancels out, plus c divided by e to the power of x squared divided by 2, which further simplifies to 1 plus c times e to the power of minus x squared divided by 2. Recall that any form like this, so a reciprocal of a power is equal to that power with a negative sign. So what we have actually found right now is an expression for y as a function of x. Note that we have some kind of initial condition, so some kind of a constant that determines also the equation, but we can solve for it if we are given adequate values. Okay, so now let's try to check a bit more applied example, and this is example number 2. So if you are planning to go and pursue the engineer's career, especially chemical engineers, this example might just as well tell you if this is something that you would actually enjoy. Of course, it's not going to be one-to-one the same in real life, but I suppose it would be pretty interesting to solve it. So let me quickly rearrange it. So we have the following task. I know that my writing is not perfect, but we have a chemical engineering question of the outlet concentration from a continuously stirred tank reactor, CSTR, for first order reaction. And now it is not written here, I suppose. No, it is not written here. So let me quickly rewrite the expression. The formula for that situation looks in the following way. dc dt is equal to fv divided by v times c in minus c, and this is all minus kc. So let's quickly define the variables. C is the dependent variable, and this is equal to outlet concentration of the reagent in time. T obviously is time. Phi V is nothing else than volumetric flow rate. We will assume it to be constant, same as V, which is the volume. And of course, C in will be inlet concentration, and K is the reaction rate constant. So what is important to note is to check what is the constant, what is an independent variable, and what is our dependent variable. So this is the dependent variable, so the equivalence of of y, same here, and of course here. And now this is our independent variable. The rest is just a constant. So how I would actually approach this problem is, first of all, open all the brackets. So we know that dc dt will be nothing else than the volumetric flow rate times the inlet concentration minus the volumetric flow rate divided by volume times the outlet concentration, and this is all minus K times the outlet concentration. Now what we want to have is we want to achieve a form that we are well familiar with. So the following form. To do that, we need to get all the terms with our dependent variable to the left-hand side, simply by adding it. So we can add on both sides this term, because it contains our dependent variable, and the other term, which also contains our dependent variable. So we are left with this expression, plus, let me already factorize the form, equals to a constant, simple constant, volumetric flow rate divided by volume times the inlet concentration of the continuously stirred tank reactor. Now, please do note that this is the expression that stands next to our dependent variable. So this is our P of x. So now, in the following step, what we want to do is calculate the integrating factor. Actually, not of x, but of time. So this is e to the power of volumetric flow rate divided by volume plus the rate constant integrated with respect to time. This is just a constant, so we can very easily calculate it as e to the power of flow rate divided by v plus k times t. Once again, I'm skipping the constant at the end, and we can now multiply both sides by this expression. So what we will get, dc dt times the exponent volumetric flow rate divided by volume plus k times t plus the dependent variable times this expression right here times the integrating factor, volumetric flow rate by volume plus k times t equals to the right hand side multiplied with the integrating factor. Let me quickly copy it and paste it. Let's make some more space so that it looks a bit nicer. Okay, just like that. And this is, of course, times the e to the power of this whole expression, so plus k, and let's make a tiny bit more space. This is multiplied all by t. Okay, looks scary, but once again, it's very much doable, because we can, from the previously determined product rule, say that this is nothing else than d over dt of this integrating factor times the dependent variable. So c times e to the power of the volumetric flow rate divided by volume plus k times the time. And this is equal to nothing else but just volumetric flow rate divided by volume times Cin, which I remind you is a constant because we have a fixed inlet concentration, times this whole exponent times T. Okay. Now once again we can now separate the variables very easily, just multiply by dt, and we are left with this expression. Okay, and on the other hand side, we have volumetric flow rate by volume times the inlet concentration times our actual function, so times this, and with a differential with respect to time. Wow. Now let's already take the integral of both sides. One side, other side. And please do note that this is just a constant, so we can easily take it in front of the whole integral. Okay, just like that. And now, once again, the rule applies. We are differentiating with, we're integrating with respect to some kind of a variable. So this is C times e to the power of flow rate by V plus K times T equals to this constant that we have right here, times, and now please do note that if we have some kind of a integral of a linear function, the result is just going to be 1 over a times the antiderivative with the inner function maintained plus the integration constant c. So what do we actually have? We have this crazy expression, 1 divided by flow rate divided by volume plus k times e to the power of volumetric flow rate divided by volume plus k times t plus c. Okay, so now once again we can divide both sides by this expression to simply clear out everything and get our final concentration expression. So we know that right now the concentration as a function of time will be nothing else than volumetric flow rate times the inlet concentration divided by the volume and further divided by the volumetric flow rate divided by volume plus the rate constant. And now notice that here this just cancels out. And I also noticed that this C may be a bit misleading, so let's call it C1 as a constant. So we have this plus C1 divided by this whole integrating factor, which we can simply duplicate and put in here. And once again, we apply the rule that 1 over a to the power of n is equal to a to the power of minus n. So we can say finally that our concentration as a function of time will be nothing else than this crazy expression. Volumetric flow rate divided by volume plus k plus C1 times e to the power of minus volumetric flow rate divided by volume plus k equals to times t. Okay, so if we very quickly note down that Fv divided by V plus k is some kind of constant, let's call it gamma, we can simply write that this is Fv times Cn divided by V times gamma plus C1 e to the power of minus gamma t. And this is our whole answer. Now, to calculate everything precisely, we would need some more data. For example, the initial conditions. So we would need to know how to calculate C1. For that, we would need to determine what is the concentration at some given time. Then we can substitute everything and simply get our answer. So to very quickly go over all the material that we have covered, if you have the exponential, the integrating factor, what we simply do, we determine it as the function that stands next to our x. We calculate this expression, multiply both sides of our differential equation by this term, find the product rule between the functions on the left-hand side, and simply integrate everything out, move to the other side, and get our answer. I really hope that this video has helped you a lot. I know that the mathematics is a bit hard behind it, but trust me, a couple of exercises and you will be going through it very, very swiftly. Thank you very much for your attention.